so we have a solid understanding of the properties and methods that the built-in character controller has available. And now we actually want to get our character moving and tie that together with animations. Not a problem. Today we're going to go through the full process of adding animations and movement to our character, and we'll do so using Unity's new input system. My name's Nikki, this channel is iHeartGameDev, my channel all about game development. I'm super excited to announce that this video is made possible by all of you with the channel's new Patreon account. Now, let's get started. This project will be broken into 3 distinct sections: setting up the animated character with its animation controller, setting up the new input system, and programming the character movement with the animations using the new input system's code. Feel free to skip around with the timestamps and adjust the playback speed, and patrons can now access these project files directly through Patreon. Thank you so much for your support. Let's start today's project by heading over to Mixamo.com and downloading 3 different animations: an idle animation, walk animation, and a run animation. We'll go ahead and use our usual settings that have been previously explained in the Mixamo to Unity tutorial. We'll also need to be sure to check the in-place checkbox. Opening a brand new Unity project will now import the packages that we need. In the Package Manager, we'll select Unity Registry and find, download, and import the new input system. Once that's complete, we'll switch to My Assets, and we'll download the Jammo character model featured on MixAndJam. A link to Jammo on the Asset Store will be in the description, so you can add it to your assets too. Next, let's create an animations folder, and then import our recently downloaded animations. And as shown, I've gone ahead and made a small environment that will be great for testing our character movement. Now, in order to use the imported animations with our characters, we need to convert them to humanoid. Selecting all 3 of the animations, finding the Rig tab in the inspector, switching the animation type to humanoid, and pressing apply, all 3 of the animations will be converted to humanoid animations. What this means is that all the bones in each animation have been remapped to the reusable humanoid structure of Unity's Mechanim animation system. And we'll also want to properly set up each animation in the Animations tab. Let's first be sure that each animation is properly titled. Occasionally, the animations from Mixamo are titled Mixamo.com, so we can name them accordingly and press apply. We'll also want to be sure that the loop time checkbox is checked, as this is what has the animations repeat. Unity sometimes modifies the direction the character is facing. To fix this, we'll modify root transform rotation, checking bake into pose and setting based upon to original for the 3 animations. Great! Animations are humanoid and ready to be used. Let's add Jammo to the scene. In the Assets window, we'll find the Jammo model in the Models folder of the Jammo package. The Jammo model will need to be converted to humanoid just like our animations. This will generate an avatar from the model, storing the properly formatted bones, and allow the model to use the humanoid animations. Now, we can drag Jammo into the scene and center the character at the world origin. Just to test, we can press play and we'll see Jammo inanimate and just standing there. Let's get Jammo animating. By default, models that have been converted to humanoid will come with the Animator component already attached and the avatar inserted. As a refresher, this component is required for animated game objects and hosts the Animator controller that will control our 3 movement animations. Next, in the Animations folder found in the Project window, we'll create a new Animator controller by right-clicking, going to Create, and selecting Animator Controller. We'll title it Character Animation Controller. We'll then drag that into the reference box of Jammo's Animator component. In play mode, Jammo still doesn't animate just yet. We need to add the animations to our Animator controller. Double-clicking on the Animator controller will open up the Animator window. Here we can create our first animation state by right-clicking, selecting Create State, and Empty. We'll title this animation state Idle, and then we'll make 2 more titled Walk and Run, as these will handle the respective animations. We can change the default state to Idle by right-clicking and selecting Set as Default State. We will then want to create transitions between these 3 states by right-clicking each, selecting Create Transition, and connecting them. Currently, we don't have anything that will cause these 3 animation states to transition from one to another. we need to create our animator parameters. For this tutorial, we just need two Boolean parameters, isWalking and isRunning. Once created, we'll modify the transitions. Let's disable hasExitTime, which will ensure that the transition between each state is immediate. And then we'll set our transition conditions. isWalking needs to be true for the transition from idle state to the walking state, and isRunning needs to be true for the transition from walking to running. We can set the same transitions in the opposite direction, but the required condition will be false instead. And lastly, we need to add the proper animations to each animation state using their own reference boxes. Entering play mode with our character selected in the hierarchy, we can now modify the isWalking and isRunning booleans in the animator and see the results. Step 2 in this tutorial is to set up our project with the new input system. We already downloaded the new input system package, so we are ready to get started. In our project window, we'll right-click, go to Create, and select Input Actions. Let's title it PlayerInput. This asset is how we can customize player input for our entire game, from UI interaction to vehicle controls to character controls. Double-clicking will open the Input Actions window in the editor. Here, there are three sections: Action Maps, Actions, and Properties, all three of which are interconnected. Action Maps can be seen as collections of actions, each action being some type of input from the player that will return data for us to use, and each action has properties, which are modifiable in the Properties section when actions are selected. This will be easier to understand with today's example. Pressing the plus button, we'll title the action map Character Controls. Now we can create actions that will be stored within the Character Controls action map. Let's title this new action Move. Now that we have the action created, how do we use it? When selected, we'll see its current properties divided into three submenus: Action, Interaction, and Processors. The Action Type property allows us to choose between Value, Button, and Pass-Through. Each option determines what controls we can possibly assign to the action, and ultimately, what the return value for the action will be in our code. For the Move action, we'll select Value, and we'll then be presented with a control type, with an additional dropdown with many options. Typically, character movement is handled with WASD or a joystick, and these values can be stored within a vector too. So let's set that for the control type. Interactions will impact how we want the player to use the action. For example, how long the button needs to be pressed to be triggered. But we won't be needing these for today. And processors can be used to modify the return value of an action. For today, we'll need to use normalized vector 2. This will prevent a frequent issue where our diagonal movement can be faster than our forward and side movement. This processor ensures that the max vector length is 1. We are now at the point where we can start specifying what controls we want to tie our move action to. Ideally, we are able to use WASD or the left joystick on the controller. The new input system makes this super easy with bindings. We'll notice that when we created the move action, there was also an item right below it titled No Binding. Selecting it, we'll see the properties window change. Now we have the option to select the binding. Pressing on the binding dropdown, we can either search for the input we're looking for, or we can use the listen button, which will find any options dependent on the next button pressed. Oh, and it's worth noting that all the control options will be filtered to options that return vector 2s because of the option type we chose earlier for this move action. Now, if we connect the controller, we can press listen and move around the left stick. We'll see and select the left joystick option to set the binding. Awesome. We'll also notice that the binding has its own interactions and processor options, which are specific to this binding. But again, there's no need for interactions today, and the processor is actually inherited from the action. With the left stick binding set up, we're almost there. How about we also get the binding for keyboard controls, WASD? To do this, we'll create a new binding underneath our move action by pressing the plus button next to the action. Here, we'll find the option for the Vector 2 Composite. A Vector 2 composite allows us to map any buttons we want to the 4 options available in a Vector 2's up, down, left, right D-pad configuration. For up, we'll select and bind the W key, and go ahead and do the same for down, left, and right with S, A, and D keys respectively. And that is the process for setting up actions and bindings. Let's make one more real quick. Pressing the plus button, we'll title this new action Run. For this, we'll leave the action type as a button. Buttons return Boolean true or false values depending on if the keypad or the gamepad button is pressed or if it's not. Let's set up two bindings, one for keyboard, left shift, and one for controller, left bumper. And just like that, we have our move and run actions set up. We're just one last step away from being able to use the new input system in our code. Back in the project window, we'll press on the player input actions asset. When selected, we'll see the option in the inspector to generate C# class. Let's check this box and press apply for Unity to generate a script of our player input action. This will make it much easier to access in our code. Okay, we are ready to code. If you are brand new to coding, it's important to understand everything that we type is case sensitive and needs to be exactly the same to get the exact same expected results. But don't worry, with more experience, you'll be able to modify and refactor where you see fit. We'll try to be as beginner friendly as possible, and this can serve as a solid starting point. To start, we'll go ahead and attach a new script to Jammo. Selecting Jammo and pressing on the add component, we can type in script and select new script. Let's title our script Animation and Movement Controller, and then double click to open the script in our code editor. Now, let's start getting control of our character over to the players. We'll declare a new reference variable, PlayerInput, of type PlayerInput inside the scope of the class. PlayerInput being the class that we just generated with the checkbox in the inspector. Now, a declaration doesn't do much. We're basically just saying this variable that we've titled PlayerInput is going to be this kind of class. We need to actually set this variable to an instance of PlayerInput so that we can use it. Let's set this variable inside of a new function, the awake function. The awake function is another lifecycle method, like start and update, that is run even earlier in the lifecycle than the start function. It's the perfect place to set our reference variables to instances like we're doing here. And while we're at it, we won't need the start function today, so let's just delete it. With this reference in place, we can now access our action maps and actions from earlier. How can we properly do this? In this tutorial, the answer is callback functions. A callback is set up to be executed when certain events take place. For example, when a key or button is pressed or the analog stick is moved, then the callback function will be invoked. We will set our callbacks in the awake function right below where we just set the player input reference. We can start by writing PlayerInput.CharacterControls.move.started. This code navigates us into our character controls action map, into the move action, and says, "Okay, Unity, listen for when the player initially starts using this action." Based on the bindings that we set up earlier, this would occur either when the player presses the W, A, S, or D keys, or starts to move the analog stick. Okay, next we'll add +=CTX, or context. This will essentially give us access to the current input data when the started callback occurs. And finally, =, and some brackets. Inside of these brackets, we'll be able to use the context argument and start checking to see what keys are being pressed. Let's give this a test. Typing debug.log and passing in context.readValue with vector2 as the argument, we can show the input in the editor console. We use vector2 because that's the option type we chose when setting up the move action. Heading over to play mode and trying to press our keys, we'll immediately notice that it's not working. But why? With the new input system, each action map actually needs to be enabled and disabled. Back in our code, we can easily fix this using mono behaviors on enable function. We'll write PlayerInput.CharacterControls.enable. And we can then do the same for the onDisable function so that if the script is ever disabled, our game won't continue listening for the player's input. Now in play mode, we'll see that when we press the W, A, S, or D keys, the vector2 will be logged to the console. W is 1 and S is -1 on the vector2's Y value, and A is -1 and D is 1 on the X value. With access to this vector2 that corresponds to the player's input, let's put the data to use. We can go ahead and declare 3 new variables at the scope of the class. A vector2 called current movement input, a vector3 called current movement, and a boolean is movement pressed. Inside of the brackets of the callback, we'll write current movement input is equal to context.readValue vector2. Now we are storing these values in our code. And immediately after, we are going to set current movement X's value equal to current movement input X's value, and current movement Z to the current movement input Y value. We assign to X and Z because the player controls the movement on the X and Z axis. As for the isMovementPress boolean, we know that if the player is pressing any of the keys to move Jammo, the X or the Y value of the vector2 is going to be greater than or less than 0, meaning it's not equal to 0. So what we can do is set the isMovementPress boolean equal to that exact logic, writing isMovementPress is equal to currentMovementInput.x is not equal to 0, or currentMovementInput.y is not equal to 0. Great. We have the current player input accessible via our new variables. How do we get our character actually moving? Of course, this series is covering Unity's built-in character controller, and after learning last episode about the move and simple move functions, it's time we actually use them. To do so, let's head back to the editor and attach the character controller component to Jammo. Be sure to recenter the collider to fit Jammo properly. With that, we can jump back into the code and add a new variable. Keeping it simple, we'll declare a variable character controller of type character controller. And just like before, in the awake function, we'll get access to this component when Jammo is first initialized by setting character controller equal to getComponent, passing in the character controller class type as the argument. GetComponent will find the attached character controller component. Okay, we have both the player input stored and access to the character controller. We have what we need to start getting Jammo moving. In the update function, we'll write characterController.move, passing in our constantly updated current movement variable. Entering play mode and pressing any of the 4 keys, and we'll see Jammo immediately fly off the screen. Let's take this back to our knowledge of the update function and our movement function. Update is called every single frame, so if our game is running at 60 frames per second, it's called 60 times. And in every call, we have our move function moving the distance of the vector3 we are passing in. So if we press forward and the z value of the vector3 is 1.0, then our character will be moving 60 units forward per second. To solve this issue, we can multiply our vector3 by Time.deltaTime. As a reminder, Time.deltaTime is the amount of time since the last frame. In other words, a fraction of a second. Testing this new solution, we'll see our character now slow down to a consistent and expected speed. Awesome. But wait, when we let go of the keys, Jammo isn't stopping. What's up with that? Let's take a look at our callback. Started is specifically called when the input system first receives the input, but that's it. If we want to track when the key is let go, we need to use the canceled callback. So if we copy and paste our callback and all of its logic, then rename started to canceled, we'll now be able to see when the player releases the key. This works great for keyboard, but controllers have a little more available motion. There are in-between values from 0 and 1. For this, we can use one more callback, performed. Perform will continue to update the changes in the player's input. Now, rule number 1 of programming is don't repeat yourself. And here we have the same code being used 3 times. Let's create a function that will handle this logic. We'll call it onMovementInput. It will accept an argument called context of type inputAction.callbackContext. And then inside of that function, we can paste the logic that we had used in our callbacks. In order for this to work though, we will need to add the namespace UnityEngine.InputSystem for Unity to recognize the callback context type. And now, instead of writing the logic 3 times, we can simply pass this function. Back in play mode, we'll now see Jammo move and stop as we continue to press the different keys. But as we can see, movement and animation are 2 different problems to solve. Jammo seems to be stuck in the idle state despite the character controller moving. This is because we need to tell the animator when we are walking and when we are not. Luckily, we already know that, so let's grab access to the animator component attached to Jammo and tell it the info. Below the character controller, we can declare a new variable animator of type animator. And again, in the awake function, we can set animator equal to getComponent of type animator. With access to the animator, we can now check and update the animation states. Just like the character controller movement, we are going to want to monitor and update the animation states every frame, so we can do so inside the update function. But if we aren't careful, our code can start to get really messy. Let's write a new function that will handle all the animation state changes. We'll call it HandleAnimation, and we can invoke it inside of the update function. At the top of this new function, we can check to see the current values of the 2 Boolean parameters we set up earlier. is walking, and is running. We know that these parameters control the transitions and switching of animation states. Using the animator's getBool method and passing in the stringified version of the parameter name, we can now locally store their current values. And now we can set up some animation logic. To first get Jammo walking, we will write an if conditional. If isMovementPress is true, meaning a player is pressing in any direction, and the animator's isWalking value is false, then we are going to want to set the animator parameter to true, so Jammo starts walking. We'll set this value using Animator's setBool method. And then we'll write another with the opposite logic. Else if isWalking is true, but the player's not trying to move Jammo, then we need to have Jammo stop walking. Testing this in play mode, and success! Jammo is now walking when we press forward, and he stops when we let go. However, it isn't perfect. Jammo only walks in the direction that it's facing. How do we turn it? Well, there are actually multiple ways that this can be done. For today's tutorial, we are going to use what's known as a Quaternion. Quaternions are a type of number system that we'll find super helpful when dealing with rotations in 3D space, and Unity has some awesome Quaternion functionality built in. Writing a new function, HandleRotation, we can declare 3 new variables, a vector3 called PositionToLookAt, a Quaternion we'll call CurrentRotation, and a float titled RotationFactorPerFrame declared in the scope of the class. The PositionToLookAt is essentially where we are moving next. In other words, it's our constantly updated current movement variable, except we are only going to want to extract specifically the x and the z variables. Next, we can set CurrentRotation to transform.rotation, and the rotation factor per frame we'll just set to 1 for now. Below these declarations, we'll define a Quaternion called targetRotation, and we'll set this equal to Quaternion.lookRotation, passing in our PositionToLookAt variable. The built-in lookRotation method will create a new rotation for us to use based on where our player is currently pressing. So let's add that condition. And right below that, we'll use another built-in Quaternion method called Slerp, passing in the current rotation from above, our new target rotation, and the rotation factor per frame. And we'll set our transform rotation equal to this. Slerp stands for spherical interpolation. What this will do is use the Quaternions passed in as arguments and return a new Quaternion rotation based on the value of the third argument. The third argument should be a number between 0 and 1, and the closer it is to 1, the faster the spherical interpolation will be. Let's add HandleRotation to the update function and test in play mode. For our example, where we have the rotation factor per frame set to 1, it will immediately switch to the new direction. Of course, if we multiply by Time.deltaTime when setting the variable, that number will become a fraction instead. And now, it will take multiple frames to complete the full rotation. If we change 1 to a larger number, it will increase the rotation speed. Now in play mode, Jammo is able to walk around and will rotate accordingly. We have just a little more to go. Let's get Jammo running. Having already created the run action with the new input system, we can create a new callback that targets its values. We'll write PlayerInput.CharacterControls.Run.Started. And this time, we'll pass the new handler function called onRun. OnRun will expect the callback context and will update a new variable called isRunPressed in the scope of the class. And because we set the run action as a button action type, we can use callback context built-in readValueAsButton method to set the isRunPressed boolean. And just like before, we need to know when the button is let go, so we can duplicate this new callback and just change started to canceled. Now, where can we use isRunPressed? We'll first want to adjust the movement speed depending on if the player is running or not. For this, we're going to need a new vector3. We will title this last vector3 current run movement. And we will set its value the same as we are with current movement, except we will multiply the x and z values by a run multiplier with a value of 3. We can then go back to the update function where we have our move function being called, and add the condition that if run is pressed, then we invoke move with the current run movement, otherwise we keep the current implementation. testing in play mode, and now Jammo moves faster when the run button is pressed. And finally, we just need to add the running animation states. But before we do this, let's do a quick refactor. In previous tutorials on this channel, we learned about Animator parameter hashing, which is a performance optimization. So let's go ahead and replace our string versions with the two new hash variables. We'll declare them as isWalkingHash and isRunningHash of type integer in the class scope, and then assign them in awake using the animator.stringToHash function with string names we used before. Then we'll replace the strings used in HandleAnimation. Okay, right below where we set the walking conditionals, we can add two new conditionals for running. We'll check if the player is moving and that run is pressed and that they are not already running. Inside this condition, we can set the parameter to be true. And in our second conditional, we can check to see if the player stops moving or lets go of run and that the parameter is currently true. In this case, we turn off the run animation. In play mode, we'll now see Jammo is able to stand, walk, run, and rotate, and because we have the built-in character controller, we get all the benefits that it has to offer. The very last thing that we will cover today is gravity. Right now, if Jammo walks off a ledge, it will not fall. This is because we've dealt exclusively with the X and Z axes. For today's project, all we need to be concerned with is setting the Y value of our current movement and current run movement to a negative number. Let's write a function, HandleGravity, that checks to see if the player is grounded or not. If the character is grounded, because of how the built-in character controller works, we'll still need to apply some downward force, otherwise the isGrounded parameter will switch between true and false. We can call this small downward value grounded gravity and set it to be minus 0.05. And if the character is not grounded, we can set gravity equal to a much higher value, like Earth's gravity. Now we'll test in play mode and we'll see Jammo falling off ledges. We did it. Awesome job today. If you want to vote on the next tutorial that this channel covers with the built-in character controller, you can actually check out the Ultra Supporter tier on Patreon. And when we finish the tutorial series on the built-in character controller, you will decide what we choose next. As always, if you would like to join an awesome growing community, we would love to have you in the iHeartGameDev channel Discord. The links will be in the description. But that's all for today. Thank you so much for watching, and I'll see you in the next video.